All right, so this is the first of our series on online minerals, I guess. So this is going to look kind of similar to how we've talked about individual minerals in the past, except that now you just hear my disembodied voice. So we're talking about pyroxene in this video, and so you did get to look at pyroxene samples in the lab right before spring break, but unfortunately we didn't have time to kind of come back together as a class and talk about pyroxene. So that's what this video is serving to do. So our pyroxene formula is going to be something like XYSI2O6. So our silicate building block has 2 silica and 6 oxygen. And so we've got these 2 sites, an X site and a Y site. These are generally octahedral sites. And so in that X site, we're going to be putting kind of the larger atoms. We can fit things like calcium, sodium, magnesium, ferrous iron in there. In the Y site, we can put in smaller atoms like chromium, aluminum, ferric iron, ferrous iron, magnesium. So ferrous iron and magnesium can go into either site, but then when you get to things that are either bigger than those two, like calcium or sodium, or smaller than those two, like chromium, aluminum, those then have to go into these different sites. And so we've got 2 categories of pyroxene. You'll hear them referred to as orthopyroxene and clinopyroxene. And those prefixes come from the mineral symmetry. Hooray, mineral symmetry. And so orthopyroxene, as you might expect, belongs to the orthorhombic crystal class. So that's going to be where we have our 3 crystallographic axes that intersect, but each is a different length. So we have an A, B, and C axis, but they all intersect, and they all intersect at right angles. In contrast, our clinopyroxenes are going to be part of the monoclinic crystal structure group. And so these are going to have 3 crystallographic axes that intersect such that there's one set of axes that are not at right angles to one another. So it looks inclined from one direction. That's where the monoclinic comes from. You can see that our clinopyroxenes are going to have somewhat more complicated formulas than our orthopyroxenes. So the main orthopyroxene that we care about for this class is enstatite. So I'm writing it here as MgSiO3. That is the same as Mg2Si2O6, so it does have the same ratios as that pyroxene structure that's written above. It's just that because each of those subscripts is divisible by 2, we sometimes shorten it to just MgSiO3. It would be just as correct to write it as Mg2Si2O6. In the case of our clinopyroxenes, we've got 2 main ones, augite and diopside. So diopside, not terribly complicated. We've got calcium in our X site and magnesium in our Y site. But when we look at augite, we've got a lot of more complicated things going on. And specifically, we have things in sites that can have different charges. So for instance, calcium is going to have a +2 charge. Sodium is going to have a +1 charge. And so we're going to have a lot of kind of charge balancing that has to happen here. So if we have sodium in this site, in the pyroxene, then we might need to have aluminum here in this site in order to balance that out. We can also sometimes get some aluminum in that tetrahedral site as well. So these are all some pictures of pyroxene crystals. These are mostly much nicer than what you tend to see. You can actually see some very nice crystal faces here, which is pretty unusual for pyroxene. But it gives a good sense of kind of the color range and also the lusters that you see in pyroxene. So I believe you've filled out a mineral data sheet for pyroxene. So hopefully you're familiar with these physical properties. So pyroxene in general, the habit or state of aggregation that it's going to take is it's going to be fairly blocky, can be somewhat prismatic. Euhedral crystals are rare, but when they do exist, they're fairly prismatic, like the ones down here. As you can see, the color kind of ranges. It's all these earth tones, I guess. We're ranging from kind of brown to near black, dark brown, kind of bright green, kind of forest green, olive green. We've got a range of lusters too, so we've got some pretty vitreous samples showing up here on the bottom. And then there's some samples that are a bit more dull. I'd say this one down here on the bottom left and this one down here on the bottom right are more dull. You can also sometimes get a fairly waxy luster. I think maybe this green one here, middle right, has more of a waxy luster. The cleavage directions are going to be two directions at nearly 90 degrees. We'll talk about that more in a minute here. And then our hardness is medium hard, kind of just slightly less hard than glass. And its specific gravity is pretty average. It's slightly high, so it's going to be higher than things like feldspar and quartz, but about around the same specific gravity as things like olivine, so pretty typical silicate. So when we're categorizing pyroxenes, you saw this on the midterm. We have what's called the pyroxene quadrilateral. So this is exactly the same as a ternary diagram, so exactly the same as the ternary diagram that you use to categorize feldspars, except that we've kind of chopped the top half off. So we consider things in this top half here pyroxenoids. So we won't be talking much about anything that has more than 50% silicon. So down on the bottom, or 50% calcium, sorry. So down on the bottom here, in brown, I'm showing where we have our orthopyroxenes. So this is going to be where we have very little calcium in the structure, so specifically less than 5% calcium. And so we've got our pure magnesium end member over here. That's going to be our pure enstatite phase. And then we've got our pure iron end member down in the bottom right. That's called ferrosilicate. Fairly rare to find that in nature. We're usually looking more in this enstatite range. And of course, we can have things that fall anywhere along this binary between the magnesium end member and the iron end member. Once you get to greater than 5% calcium, you become a clinopyroxene. This actually happens because calcium is a bigger ion than magnesium or iron, and so in order to shove it into the pyroxene structure, you end up somewhat distorting it. And that distortion kind of forces the pyroxene crystal slightly askew, and it's that askewedness that gives it that monoclinic structure. So augite is a pretty wide field in this clinopyroxene range, and then diopside up here, that's closer to this magnesium, calcium, silicon, oxygen end member. These other ones, Hedenbergite and pigeonite, are slightly more obscure, so we won't be talking about those much in this class. So now that we've talked about crystal symmetries, I can also kind of show a bit of the different symmetries that these two types of pyroxenes have. Our orthopyroxenes, that's our top row here, so these are orthorhombic crystals. And then our clinopyroxenes, this bottom row here, are our monoclinic crystals. And so in the first column, I've tried to show kind of a three-dimensional representation of an example crystal from each of these crystal classes. And I have the axes turned on so that you can see That, for instance, the C-axis is up here going vertical through the crystal. Then we've got our A-axis and our B-axis. And because we're looking in a 3D representation, it's kind of hard to tell what angles any of these axes are actually at. So that's why now to the right, I'm showing you 3 views of the crystal. One where we're looking straight down the A-axis, and so we can see that the C-axis and the B-axis are perpendicular to one another, and we've got some twofold rotational symmetry here. Then in the second panel, we're looking straight down the B-axis, and we can see that the A and C axes are perpendicular to one another. And then finally, in this third panel, we're looking straight down the C-axis, so we're looking straight down from the top of the crystal, and we can see that the A and B axes are perpendicular to one another. So indeed, we've got 3 sets of crystal axes, and they all intersect each other at right angles. So that's what is making this an orthorhombic crystal. And since we can see from the top here that we only have 2-fold symmetry when we're looking down the C-axis, we don't have 4-fold symmetry. That means that we're looking at an orthorhombic crystal and not a tetragonal crystal. When we go to the bottom row here, so here again I'm showing kind of a 3D representation and then views straight down the A, B, and C axes. And so you can already see, just kind of looking at it, that we have less symmetry, less total symmetry elements here than we did in the orthorhombic case. So the most helpful one to look at here is going to be when we're looking straight down the B-axis, because this is showing us that the C-axis and the A-axis of this crystal are not perpendicular to one another. They're instead set at an angle. We can see, however, that the B and A axes are perpendicular and the C and B axes are perpendicular. But because we have this one set of inclined axes, C and A, relative to one another, that puts us into the monoclinic category rather than the orthorhombic category. So in terms of the cleavage planes that pyroxene displays, again, here's a 3-dimensional kind of representation of what's probably here an orthopyroxene, an orthorhombic pyroxene. And these black lines are representing the 2 directions of cleavage, these planes that are occurring at approximately 90 degrees to one another. In terms of the Miller indices, the set of faces that would represent would be the 1, 1, 0 face, because we're going to have a plane that's intersecting the A-axis, and the plane of cleavage also intersects the B-axis, but it never interacts the C-axis. So that's why we get that 0 there as our 3rd digit. So when we look along the sides of the crystal, when we look around a face that's perpendicular to the A-axis or a face that's perpendicular to the B-axis, we see these parallel cleavage lines. And you'll see that a lot in natural pyroxene crystals. When you look down the C-axis, though, from the top, you can see both of the directions of cleavage occurring here. So you get this kind of steak grill pattern, or our pull and peel Twizzler pattern there. So this now is a view underneath, looking along or looking down that C-axis and seeing that you've got 2 different planes of cleavage. So we've got the ones that are running kind of northwest, southeast here. And then we've got the ones that are running northeast, southwest, and those are at approximately 90-degree angles to one another. I think they're actually at like 87-degree angles. When we're looking at crystals in real life, frequently pyroxene does not have as nice of cleavage as that of micas or feldspars. So sometimes you have to kind of squint a bit to convince yourself that in something like this that you're seeing that blocky pattern that this prismatic cleavage is resulting in. And so, as we've talked about a bit, this cleavage pattern that pyroxenes have, it results directly from that atomic crystal structure. So these are on the bottom right here, some images that I pulled up in Crystal Viewer. So you can go ahead and pull these up in Crystal Viewer yourself. And so pyroxene is a single chain silicate. We'll be talking about exactly what that means more this week. And we're looking down the C-axis here. So we're looking at the equivalent of this picture here, except now we're looking on the macroscopic scale at kind of the interior structure of this crystal. And so on the left, I'm showing the polyhedral representation. We've got kind of these two different octahedral sites in yellow, and then it's hard to see that they're octahedral, but these kind of teal balls as well. And then we're looking straight down on these single chains of silicates. And so what you can see over on the right here is a side view of one of those single chains. So we've got a tetrahedron connected to another tetrahedron by a vertex, connected to another tetrahedron by a vertex, and it keeps going down, down like that. And so you can imagine if you were to rotate this 90 degrees so that you were looking straight down this chain, you would see this part of this tetrahedron and this part of this tetrahedron. And so that chain would be two tetrahedra across. So that's what we're seeing here. We're seeing a top tetrahedron and a lower tetrahedron. So this is one single chain, but we see two tetrahedra when we're looking from above. And so in this view on the right here, then, I have turned off everything except for the silicate tetrahedra so that you can see more clearly where those breaking points are going to go through the crystal. And you can see, so we have some wiggle in the line here, but this is because we're looking on the atomic scale. If we were to zoom way out to what we're seeing in real life, these would be essentially straight lines. And you can see that these lines, these green cleavage lines, intersect each other at approximately 90-degree angles. So here are just some pictures of pyroxene within igneous rocks. So they're generally going to be dark and blocky. The blue words here refer to words you might recognize if you've taken Geo 101. So pyroxene is going to be relatively high in magnesium and iron relative to silica. That means that it is a mafic mineral, so we're going to be finding it in mafic igneous rocks. It may form phenocrysts, those are going to be very large crystals, or it might be part of the ground mass, which is going to be kind of the background, very small crystals. And so in the upper right here, we have a gabbro. The light material is plagioclase, and the dark material is all pyroxene crystals. So you can see they're not particularly nice crystals, but they do have a fairly blocky look to them. In the lower right here, we have a basalt. This is a vesicular basalt, so all of those holes are places where gas escaped as this lava was erupting. And here, the crystals are much smaller than they were in the rock above. They may even be microscopic, but a large percentage of this rock is made up of pyroxene crystals, and that's what's giving it this kind of dark color. So this middle panel, middle bottom, is showing a zoomed in view of what looks like probably like a cut and polished surface of a rock that has large pyroxene crystals in it. So for instance, this crystal over here on the left part is a beautiful example of a blocky pyroxene crystal. So we can see very well how we're getting those kind of rectangular shapes forming in these crystals. Probably a lot of these cases where we're seeing more hexagonal crystals, we're actually seeing edges of crystal faces rather than cleavage planes. and we're probably looking down the C axis in the case of these crystals. Got another picture down bottom left here, again showing kind of blocky crystals. We're probably looking along an A or B axis, so we're probably looking at the side of an elongated crystal here. And then this rock here is showing that pyroxene need not always be black, so this is a good example of a green pyroxene, probably diopside or augite. Clinopyroxenes tend to have more of that bright green color to them. And you can really see that kind of blocky structure, especially here. So if you open this PowerPoint on your own laptop, you can zoom in pretty far on this crystal and see cleavage planes really nicely here in a way that would be much harder to do on some of these other rock samples, such as this one. All right, and so I've also put together a list of 3D models of pyroxene that I found on Sketchfab, one of the websites I showed in class. And so these, if you've got a bunch of computing power, they tend to be a little slow and kind of make your computer whir a lot. But they're really nice ways to sort of mimic being able to actually look at a rock. It's not the same as holding it in your hand, but it is better than nothing. So I'm going to show a couple examples here, not all of them, because I think it'll be better for you to just go and play around with them yourself. So let's go here, and I will show, for instance, this is a hypersthene crystal, so this is a type of pyroxene. Give it a second here. And so a lot of this is just kind of massive, it's pretty anhedral. But there are some places where you can see that kind of blocky structure. So this is a nice part here where you can see some of that cleavage, that kind of blockiness. So again, we're probably looking at the side of this crystal here. So we're seeing those parallel traces of the cleavage. Again, you can kind of rotate it around. Look at these different faces. So here's another place where we've got some nice cleavage that you can really see here. So you can start to get a better sense, and you can zoom in a bit more and see the way that these these cleavage planes are interacting with each other. So everything we're looking at here is probably a cleavage plane, not a crystal face. And so we're probably the clearest cleavage plane to see here is the one just kind of at the top of the sample. So you can see this kind of stair step like there, and then chunk down a step, chunk down a step. So that's probably our main cleavage plane right there. So it's rare to see very nice euhedral pyroxene. We're usually looking at cleavage faces or kind of blocky masses. But this is just a beautiful monoclinic crystal. And it's so nice. You can really see these crystal faces. And what I really appreciated about it is that you can actually rotate it like this. So we're probably looking along the B axis here. So we'd have the C axis running vertically through the crystal. And then our A axis would be running something like this, and we're looking straight down that B axis. And so what you can see is that the A axis that's running along this way and the C axis are not perpendicular to one another. And so that's our monoclinic symmetry here. So we can see that we've got a twofold rotational axis. We could rotate around this point here in the middle, and we'd get this point to come up to this point. But most of the other directions that we would expect to be twofold symmetry in an orthorhombic crystal are not here. So if we look down from this side, this is not a twofold rotational axis, even though it has the shape that looks like it might be, because if we rotate it back here, this point is sticking up. So if we rotated, if we did a twofold rotation, we'd move this around, and the sticking up part would be on the other side. So that is not a twofold rotational axis. So this is just a spectacular example